All right, today we're going to look at the time-independent Schrodinger equation a little bit more in depth. And we're going to do, I think, two things. One thing is we're going to sort of justify, or at least see one way to view where this comes from. All right. The other thing we're going to do is we're going to look at it and try to understand how the solutions of this must work, looking at the equation. And so we're going to be able to go through and sketch the energy eigenfunctions for different kinds of potentials, which will be really helpful to us later on in the semester. And so the first thing we're going to start with is generalizing the de Broglie relationship. So we have this de Broglie relationship that says the wavelength is h over the absolute value of the momentum. Now we know that this works for a free particle for when the potential is 0. And we want to say, does it work when the potential isn't 0? Can you generalize this into situations like that? And so from this equation we can sort of see as the kinetic energy increases, the wavelength decreases, right? So as k goes up, the wavelength goes down. Well, I can look at the kinetic energy as a function of the potential. Okay, so if I'm looking at some particular total energy, then just subtracting the potential gives me the kinetic energy. And so we're going to try to develop is this idea of the local wavelength. So basically the wavelength can be different at different points, and it's going to be, just using this relationship here. Okay, it's just that now the kinetic energy is a function of position. If the potential can change, the kinetic energy can change as well. And so as the potential energy increases, the kinetic energy decreases. So we can sort of get a relationship between the potential, the kinetic, and then from that, the wavelength. And so let's just try doing this. So here is a potential that's actually pretty hard to solve analytically. And so it goes down to some point here and then comes back up. And so suppose we're trying to find a certain energy for this potential. Okay, so this is some system and we want to look at some bound state energy. Now we just want to look at here. Okay, so as we go to the right, the wavelength of the energy eigenfunction that would solve this picture, okay, what's going to happen to its wavelength? So as we go to the right, will the wavelength increase, remain the same, decrease? What do you think? Think about this one and then we'll talk about it. All right, so hopefully you got decreases. And so let's look at this a couple of things. So first of all, it's not super easy to get this, or to think about this right away, but the kinetic energy here is just basically the difference between the energy and this potential that I sketched out, right? So the kinetic energy is the E minus V sub x. And so you can see as you go to the right, okay, as we move to the right, the kinetic energy is going to be increasing. All right, and so then we grab our equation for the wavelength, and we know that that's basically inversely proportional. So if the kinetic energy is increasing, the wavelength is going to be decreasing. So in a case like this is exactly what we're talking about. This potential, okay, is decreasing, and so as it decreases, the kinetic energy of this system would be increasing, and so the local wavelength is going to be decreasing. And so this is the type of information you could use to help you sketch the energy eigenfunctions without actually solving the equation. The next thing we want to do is try to be able to describe the wavelength, or better yet, the curvature of our function from the functional form itself. Okay, and so the way that we're going to approach that is to look at the second derivative. The second derivative gives us the curvature or the concavity, all right, which is the rate at which the slope changes. So we can start with that. Now, that's a good place to start, but if you look at this picture over here, okay, for instance, these two plots, the yellow and the blue, right, they have the same wavelength, but they have different curvature. This one's going to have, much more curvature than the blue one would. And so we have to account for that, and one way to do that is to take this concavity and divide by the amplitude, by the function itself, okay, which will end up, this will make this independent of amplitude. And so if we take the second derivative divided by the function itself, this is going to be our measure of the curvature, or also it's going to lead us to our measure of one way to determine our wavelength. Now it's good to stop here and think about what are the dimensions of this horrible thing that we're talking about. And so pause this, think about this for a second. What are the dimensions of this thing here? Okay, so hopefully you got 1 over L squared. So I think what gets people here is just this definition of a derivative itself. So suppose I have some function f of x. We don't even know what it is, but let's just say it's some function f of x, and I take one derivative. Okay, so what that does is it's looking at how the function changes with respect to time. And so it's kind of taking a delta f of x, the delta of the function, in a very sort of hand-waving way. I'm doing delta f of x over delta x. And so the units of that are whatever the units are of the function f of x. And let's just call the units of my function f of x to be u, for instance. And so this is going to give me units of u over x, which would be length. All right? And then so if I take that, if I then say take the derivative of that, okay, so I'm taking the derivative of f of x dx with respect to x. That's going to give me the units of whatever that thing was, which is u divided by L, then divided by another L. So every derivative of position that you do, it gives you another unit of length on the bottom there. So this would be u divided by L squared. And so if I plug this in here, this would be u divided by L squared. The units of f we again had defined as u, whatever the heck that is, those cancel, and I get 1 over L squared. And so we see that this thing that we're developing to hopefully give us some way to think about the wavelength comes out as units of length squared. And so what that tells us is that naturally we can maybe think about this as being equal to 1 over our local wavelength squared and see where this gets us. Okay, and so another way to think about that here is I just said, okay, so my wavelength squared equals some c constant times the inverse of all this junk here. Now the book lets you or invites you to actually solve for this c using a nice sinusoid, and if you do, it comes out to be negative 4 pi squared. And again, this wavelength of x is defined as our local wavelength. It's the wavelength at a point. And so we're going to be dealing with wave functions that are going to be having their wavelength change as a function of position. Okay? And so now what we do is we can sort of take some of our definitions. So here, this is our de Broglie definition, and I just take this now and solve it for k. And so k equals h bar over 2m lambda squared. So again, that's the quantum mechanics here that we're talking about, okay? And we take that and say, okay, so that's my kinetic energy. Well, if I just look at conservation of energy, that's going to be E minus my potential as a function of x. All right, and then we take this beast here, which we just developed as a way to sort of look at the curvature, and we're relating that to our wavelength. So it doesn't really have anything to do with quantum mechanics yet, and so merging it with this, of course, is going to definitely make it quantum mechanical. One note is that, the texts are always a little bit different. Moore calls the energy eigenfunction psi sub e, where we've been sort of looking at them as psi with a psi n, like psi 1, psi 2, psi 3. So it's just a little bit of a different philosophy, but it's the same sort of idea. But basically what we're going to do is we're going to merge this. We're going to take this thing here, which is our definition from 1 over lambda squared, and plug it in over here. When we do that, it looks kind of like this here, which right away looks very ugly. But if we just sort of unfold this a little bit, we see that it's just the time-independent Schrodinger equation, which is nice. Okay, so if I take this, so first of all, the 4 pi squared and the h bar squared, right, that just gives us, I'm sorry, the h, remember that's an h there, not an h bar, gives me h bar squared. So this is where you can kind of, it's just getting rid of the 4 pi squared to make life a little bit easier. All right, and so we get the h bar squared. We move this negative out front because we like to have that negative here. And then what we do is we just multiply both sides by a psi sub e. Okay, and if you look at this, this is just the time-independent Schrodinger equation. So how we got this is by sort of trying to define our wavelength in terms of our functional forms, and then plugging that into our just energy conservation, and using our de Broglie relationship to make the momentum into the wavelength. That's all that we did here to sort of, again, now this is a way to justify this equation. Now we're going to look at it a little bit more in depth and hopefully try to get some ways that we can use this to help us solve some certain things, or at least just sort of, qualitatively look at our solutions and understand them a little bit better. All right, so again, we're going to spend much of the rest of the semester solving this. We've already solved this for the infinite square well, right? So we got one solution down. We're sort of going through and trying to understand that now. But let's just see what else we can sort of gain by qualitatively studying this equation. All right, and so your translation, when we say we're going to be solving the time-independent Schrodinger equation, what that means is we're going to spend much of the rest of the semester looking at differential equations. And here we talked about these, but these are two of the most important differential equations that we'll look at least right now in quantum mechanics and in physics. And so we're taking these equations, looking at the second derivative of some function and looking at the case where that equals some constant times the function. And of course here it's where it's a negative constant, here it's a positive constant. And we talked about this, and so in the top case, number 1, it'll be a wave-like function, a sine or a cosine. Okay, our complex exponentials will also work for this, but we'll see that later. And then for number 2, it's going to be an exponential, non-complex exponential. All right, and you can actually just take both of these, take two derivatives of them, and then here you'll see that it equals a negative constant times the original function, and here it equals a positive constant times the original function. That's one way to kind of view this. Another way is to take our time-independent Schrodinger equation and write it similar to that. So we isolate the second derivative, and it equals a whole bunch of stuff here times our function. So it's a very similar shape, and then this thing here, all right, becomes similar to that c we were just talking about. And so we're gonna sort of learn here that basically e minus vx will give us the sign of our c, and it tells us basically what kind of solution we're going to have, a wave-like solution or an exponential-like solution. All right, and so again, in our c function, if you remember, so if I say E is greater than V of x, and let's just look at this real quick. So kinetic energy is E minus V of x. So if the energy is greater than the V of x, if I go over to here, if energy is greater than this, then this means it's positive term in here. That's positive. And so here's a negative, and so it'll end up being the negative c. And so if this is true, all right, we're going to have the negative c f of x, which means we're going to have wave-like solutions. Another way to look at that is just in this equation here, this second derivative measures the concavity, right? This is the concavity, and so in the case where I'm on the positive side of the axis, that means my function is positive, then the concavity is negative c times a positive number, so it's a negative, and so it's concave down. If I'm on the negative side of the axis, I'll be concave up, which again gives us that idea of wave-like solutions, curves towards the x-axis. No matter where you are, it curves towards the x-axis. Okay, so that we get just again from our definition of the Schrodinger equation, and it's just important to note that this is what we call the classically allowed region, right? When energy is greater than potential, I have a positive kinetic energy, that's classically allowed. Now over here, the other side, when energy is less than my potential energy, okay, now that means we're going to have a negative in here, so negative times a negative equals a positive. And so I get this positive c. Now first of all, that's classically forbidden, so we'll talk about what this means quantum mechanically for us in a second, but this would not be allowed classically for the particle to be found here, all right, because E minus V of x would be negative, a negative kinetic energy. But what that means in terms of our concavity, this is the concavity, all right, if you've got positive function, then positive, that means that concavity is going to be positive or concave up. And if it's a negative, it's going to be concave down. So it's always curving away from the x-axis, which is another way to kind of view this exponential-like solution. All right, and so those are going to be really important to us when we're plotting. So basically, when we're classically allowed, we're going to say that it's a wave-like solution. When it's classically forbidden, it's an exponential-like solution. A couple more things we want to talk about just to kind of help us with this would be, first of all, we can look at this equation and argue that it must be smooth and continuous. All right, so why can we say this has to be smooth and continuous? Well, let's look at the smooth first. Smooth, what that means to us is that the first derivative of our wave function is continuous. Okay, so the d energy eigenfunction dx. All right, now if that's not continuous, that means it jumps suddenly, and that means we're going to have an infinite second derivative. Well, in order for this equation to be true, if our potential is finite and our energy eigenfunction is finite, that can't be. Okay, this equation wouldn't be able to be satisfied then. And so this will lead us to having a smooth solution. And furthermore, the actual wave function itself, the energy eigenfunction itself, also has to be continuous. If this wasn't continuous, then you'd have an infinite first derivative derivative, and of course infinite first derivative causes tons of problems for your second derivative. Okay, and so just for this equation to actually be valid at all points, it tells us that it has to be smooth and continuous. We've talked about this before, but we didn't really break it down this much. All right, and the last thing we want to talk about is the amplitude, so the actual size of our wave, right? So when we're actually sketching these wave functions, you got sometimes like there'll be larger amplitude and smaller amplitude. And the way this works in general is the local amplitude of the wave-like part of the solution decreases as the value of E minus Vx. Again, E minus Vx we can think about as our kinetic energy. So it decreases as the kinetic energy increases. All right, now what does that mean? Well, classically, a smaller kinetic energy implies that the particle would spend more time in that region. If you're going slower, you're going to spend more time than if you're going faster. And so quantum mechanically, this is manifested in a larger amplitude. Okay, so there'll be a larger amplitude in the places where my kinetic energy is smaller. All right, and this is a manifestation of this idea that classically you'd be spending more time there. All right, now the book does this, but this is basically just my own version of what the book is doing, and this is our rules for sketching these energy eigenfunctions. This can be really handy when you come into a new situation that you're it's a little bit foreign to you. You can go through and use these, and you can guess or sort of sketch what the solution should be. Okay, and just a quick summary is the solutions are wave-like when it's classically allowed, exponential-like when classically forbidden. Okay, we talked about that. The curvature of the solutions increase as the kinetic energy, or as the E minus Vx, as that thing increases. So classically allowed, what that means is the larger E minus Vx is, the larger your kinetic energy, the shorter your local wavelength is. That's the first thing we started talking about. In the classically forbidden region, okay, we're going to see that the larger E minus Vx is, the shorter our exponential tail is, and we'll talk about this in a second. We just discussed how the amplitude of the wave-like part of the solution decreases as the value of E minus Vx increases. So basically, again, it's like you're thinking about the kinetic energy. Wherever the kinetic energy is smaller, you're going to have a higher probability of finding the particle there. From the differential equation itself, we can show that the solutions must be continuous and smooth as long as the potential is finite. And our solutions, to be normalizable, this is something we're pulling from Griffiths, approach zero as we go to positive and negative infinity. And the last thing, we've seen this with infinite square well, but it'll be true in general. Our energy eigenfunctions for bound states, for bound quantons, have an integer number of bumps in the classically allowed region. The more bumps means the more energy for those things. Now let's go through and look at an example. All right, so this is an example right out of the book, and it has a similar potential to one we were kind of looking at. So our potential comes over here, comes down, and then increases slowly and steadily up to this point over here. And my energy is this line right here. So these would be my so-called classical turning points. Okay, the place where the classical particle would have to be in between. Now, of course, quantum mechanically, we see that that's going to be a little bit different, but we'll talk more about that. So just a couple things. First of all, our kinetic energy is basically, you can sort of think about it as the difference between the energy and the potential. So basically, as I go this way, my kinetic energy is going to be decreasing. Okay, which means, first of all, the amplitude gets larger. So it's more likely to be found on the right side than it is on the left side. It also tells us about the wavelength. The wavelength will increase as we go to the right. You can see that too, right here. This wavelength, maybe here, this wavelength 2 is going to be bigger than this wavelength 1. Okay, so that's a couple different things that we've been talking about. The other thing is here, so this is the classically allowed region, classically allowed, and then this is our classically forbidden. And so you can see that it's wavy in the middle in the classically allowed, and it's exponential tails in the classically forbidden. And one thing just to sort of talk about is, if you look here, they talk about the short tail or the long tail. This is something that's a little bit confusing. And basically, first of all, this whole thing is confusing, that there is some sort of amplitude for the particle to be found in the forbidden region. But if you look on the left side, here's the left side, here's the right side. And what I would say is, if you look here, the difference between the potential and the energy, okay, so sort of how classically forbidden it is, okay, that difference is much bigger on the left side. And so I sort of think about it as it's very classically forbidden on the left side, and then maybe a little bit classically forbidden on the right. And so if it's very classically forbidden, the tail is very small, and there's a very sort of small amplitude for it to be there. Whereas over here, we're on the right side, where it's, it's a little bit classically forbidden, there's a lot longer tail. And of course, the extreme case is what we've been talking about, the infinite square well, where that sort of difference there is infinite, and there's essentially no, there is no amplitude for it to be in the forbidden region. Now that's on physical, but as you get this thing, if this thing here was to get larger and larger, this would get very, very close to having no tail. Okay, so those are just a couple of the things that we're looking at here in sketching these. Let's look at a clicker question here. So here we have the real part of a stationary state wave function of a particle with energy E, and it's shown below. Assume E is greater than v sub x for all x. That makes sense. It's wavy. In which region is the potential the largest? So take the rules we have and try to think about this one. All right, so for this one, we actually have two ways to think about this. And so we have this equation we've been using. The kinetic energy is my energy minus v sub x. So first of all, for any energy eigenfunction, right, we know, and again, a stationary state is just another way to say energy eigenfunction. For any energy eigenfunction, it's got to be a constant energy. So the energy is going to be the same. Okay, and what's going to be changing with the kinetic energy and the potential? Well, we know that when the particle is going the slowest, it's most likely to be found there. And so if you just look at the amplitude, okay, this here is the highest amplitude, and so I would say that this is going to be the lowest kinetic energy. All right, and then over here, if you look at region 1, this is where it's least likely to be, and so I would say that's the highest kinetic energy. Now this question is asking about the potential, and so if I solve this for the potential, I would get E minus kinetic energy. And so what does that mean to us? Well, the potential is going to be the largest when the kinetic energy is the lowest, right? Because the energy is the same value in all three places, and so if I subtract the lowest amount of kinetic, I'm going to have the highest potential, and that would be in region 2. Now you can also think about this in terms of our wavelength. Okay, so the wavelength we know is going to look at something kind of like this here, right? So again, the same idea. My wavelength is inversely proportional to my kinetic energy, and so in region 2 you have the biggest wavelength. So it's the biggest wavelength, which means you're going to have the smallest kinetic energy. And so the smallest kinetic energy again is going to give us the biggest potential energy. All right, so give this one some thought. This stuff, I think, at first takes some getting used to. There's 2 questions on the PCQs about this that we'll talk about in class.